Hey, welcome. You've seen a dancer move with incredible grace, or an athlete explode with power, right? It's just amazing to watch. But what if we could actually get under the hood and see what's happening? Today, we're going to dive into how we take that physical art and turn it into the cold, hard language of science. It's pretty cool. Let's get into it. So yeah, that's really the big question, isn't it? How do you measure something that feels like, well, art? When you watch a high jumper arch their back over the bar, it's just pure poetry. But for a coach, for a biomechanist, it's a puzzle of physics. How do you possibly connect those two worlds, the art and the hard data? Well, it's actually pretty straightforward, but incredibly powerful. We turn it into science. We translate that physical motion into the language of kinematics, which is just the science of how things move. The whole point is to take what we can see, what feels intuitive, and transform it into real, solid numbers that we can actually measure, analyze, and, most importantly, improve. All right, so here's our game plan. First, we'll talk about how we even model the human body for this stuff. Then we'll get into the actual language of motion. After that, we'll see how to track the center of mass and, my favorite part, decode how our joints move. And we'll wrap it all up by looking at why any of this matters out there on the field or in the clinic. Okay, section 1, modeling the human body. You can't just throw a bunch of sensors on a person and expect the data to make sense. The human body is way too complex for that. So the first step, and it's a crucial one, is to simplify. We have to create models that act like a blueprint, giving us a framework to understand all that motion. So let's start with the absolute simplest model, the particle model. Think of it like a GPS dot on a map. We're essentially treating the entire human body as one single point in space. So for that high jumper, we're not worried about their arms or legs flailing around. We're just tracking the path of that single dot, their center of mass. It's perfect when all you care about is the big picture, that overall trajectory. Okay, that's the basic dot. Now, let's add a layer of detail. The next step up is the rigid body segment model. Here, we start breaking the body down into its parts, the thigh, the forearm, the trunk. Each one is treated like a solid, unbending link. You can almost picture it like one of those wooden artists' mannequins. The important thing is, these segments don't stretch or bend. And this model, it's literally the foundation for pretty much all serious 2D and 3D analysis we do today. And finally, we get to the whole shebang, the multi-segment linked model. This is where we take all those individual rigid parts and connect them together at the joints, creating a full chain. Now we're not just looking at a thigh or a foot in isolation, we're looking at the body as an entire system. This is the model that lets us really dig into coordination. How does the movement of the hip affect the knee? How does it all work together? So just to recap real quick, you've got the particle model for the simple big picture path, you've got the rigid body model when you need to look at individual limbs, and you've got the multi-segment model when you need to understand how it all links up. It's all about picking the right model for the question you're trying to answer. All right, section 2, the language of motion. So we've built our stick figure, our model. Now we need the words, the grammar, really, to describe what it's doing. This is where we get into the absolute fundamentals of kinematics: displacement, velocity, and acceleration. And this language is built on 3 key ideas. First, you have displacement. That's just a fancy word for the change in position. Where did it go? Then you've got velocity. That answers the question, how fast is it going? And finally, acceleration. That's all about, is it speeding up or slowing down? Simple as that. Now this is where things get really, really cool. These 3 concepts aren't just separate ideas. They are deeply connected through calculus. Check this out. If you graph an object's position over time, the slope of that graph, how steep it is at any point, literally is its velocity. Then, if you take that velocity and graph it over time, the slope of that new graph is its acceleration. It's this beautiful cascade where each concept is just derived from the one before it. So you might be wondering, okay, how does a computer actually do that? How does it find the slope? Well, it uses a really clever method called numerical differentiation. For any given point in time, it doesn't just look at that point. It looks at the position data from the moment just before and the moment just after. By taking the difference between those 2 points and dividing by the time between them, it gets a super accurate estimate of the velocity right at that instant. It's how we turn a fire hose of raw position data into something meaningful, like speed. Okay, section 3, tracking the center of mass. Let's put this language to work on something we can all visualize, the body's center of mass. It's basically the body's average position, its balance point. It's this imaginary spot where all your mass is, like, concentrated.
And what's amazing is that when we track the path of that center of mass, different movements create their own unique signatures. Take a look. For walking, you get this smooth, rolling up and down wave, a sinusoidal pattern. But for a jump, bam! You get this perfect, clean, parabolic arc. It's exactly what you'd see in a physics textbook. These graphs are so precise, they immediately tell you the story of what's happening.
All right, section 4, decoding joint movements. So tracking the center of mass is great for the overall picture. But let's be honest, the real magic, the complexity of human movement, happens at the joints. So now we're going to zoom in and see how our limbs actually coordinate. One of the most fundamental tools we use for this is an angle time curve. It's exactly what it sounds like. We're just plotting how a joint's angle changes over time. You can look at a graph like this for the knee during walking, for instance, and pinpoint the exact moment of maximum bend, that's flexion, and the exact moment it's most straight, that's extension. It gives us a super precise map of what one single joint is doing. But that only tells us about one joint at a time, right? And that's not how we move. Our bodies are like an orchestra with everything working together. So the next big question is, how can we possibly see the relationship between two different joints, like how the hip and the knee are coordinating?
We do it with something called an angle-angle plot, and these things are just brilliant. Instead of plotting a joint angle against time, we plot the angle of one joint against the angle of another joint. So as someone takes a step, the constant back and forth between their hip and knee angle traces out this amazing, continuous loop. And that loop's shape? That's the signature of their coordination pattern. It's fantastic. And that loop is telling us so much. For instance, if the loop was just a straight diagonal line, it would mean the two joints were moving perfectly in sync, or in phase. They both bend and straighten together. But when you get this oval or circular shape, it tells you they're out of phase. As one joint is bending, the other is straightening. That pattern is basically a fingerprint for how the body has decided to solve a particular movement problem.
Okay, last section, why this analysis matters. We've got all these fancy models and these incredibly detailed, accurate graphs. But so what? Why do we do all this? What's the real-world application here, from the lab to the playing field? This is a perfect example of why it's so powerful. On the left, you're seeing the angle time graph for a typical, healthy knee during walking. Now look at the one on the right. It's clearly different, right? A physical therapist can look at that and immediately see that the peak flexion is lower, or maybe it's happening at the wrong time. That could mean anything from an injury to stiffness to the person just walking carefully to avoid pain. The graph makes the problem visible. And really, that's the whole point. By having a normal pattern to compare against, we can do some amazing things. We can pinpoint a tiny flaw in an elite athlete's pitching motion. We can help diagnose why a patient is having trouble walking. And maybe most importantly, we can track their rehab progress with actual numbers, not just guesswork. It's all about making the invisible visible.
So we've gone on this incredible journey from just watching someone move to building a model of them, to creating these detailed graphs that let us understand that motion on a completely different level. And as our technology, the cameras, the sensors, the software gets better and better, you just have to wonder, what's next? What new insights into human potential, into the very limits of what we can do, are we about to unlock? It's an exciting time to be asking these questions.